This is like a puzzle. We're going to break this down into parts, always starting at the top of the page and working left to right. When I say page, I mean the grid here. So this term is 3x to the third. If we write things in standard form, highest degree to lowest degree, and then make sure that we include a placeholder of 0 if any of these don't show up, then we know that the sum of the terms here is that first term. The sum of the terms here is the second term. The sum of the terms in this diagonal is the next, and so on. So we're taking this polynomial, which is represented by the sum of all these parts, and dividing it by x and a positive 5. Put 3x to the third into the first square, or we call it rectangle. Now we know this information, so we have this, we don't know that. Well, divide 3x to the third by x, and now we know that we must have 3x squared. 3x squared times x is 3x to the third. Now that we have this information, we can fill in this information. 3x squared times 5 is 15x squared. The sum of this diagonal is equal to that value there. 15x squared plus something is 22x squared. That something has to be a 7x squared. Now that I know this information, I can find this information. Because 7x squared divided by x gives me a positive 7x. I can now find out what this is. 7x times 5 is 15x. And not 15x, but 35x. So now this sum of this diagonal, 35x plus this value, must be equal to 38x. Now that I have that information, I know that 3x divided by x is a 3. I find the product of 3 and 5. I get a positive 15. This term is equal to that term, so I do not have any remainder. There's nothing left over. X plus 5 goes into this polynomial this many times, you can say. This is the other factor. There's no remainder. There's nothing left over. This ends up being the same. Okay. Next question. Is 3x squared plus 7x plus 3 factorable? The answer is yes. Is it going to be easy? The answer is probably not. But can I find solutions for x, knowing that this is a quadratic? Can I find solutions for x? Is there anything else I could use? Well, if this is A, B, and C, then I can use the quadratic formula, which says x equals negative b plus or minus square root of b squared, subtract 4ac all over 2a. That'll give me my other two factors that with this factor, x plus 5, gives me a degree 3 polynomial. I know negative 5 is one of my roots. Negative 5 plus 5 is 0, so that's going to give me one of my roots. I don't yet know without graphing or using this information to find the other two x values, the two x-intercepts, whether they are real or non-real. So let's take a look at the next question. So this is my next problem. Set up the same way. I have a grid, I'm dividing by some binomial, and my factor, my answer, my solution is going to be up here. This polynomial in the numerator is represented by the sum of all these parts. Again, first step, put your first term into that first square. Find the answer to x to the third divided by x. My answer is x squared. Now that I know that term, I can find this term. X squared times 4 is 4x squared. $4x squared plus this term on the diagonal is going to be equal to negative 1x squared. The sum of negative 5x squared and 4x squared gives me a negative 1x squared. Factor out an x from this term. Now that I know that term, I can find this solution. Negative 5x times 4 is negative 20x. The sum of these on the diagonal is equal to negative 34x. I need another negative 14x. Factor out the x and I get negative 14. And then negative 14 times a positive 4 is 4 times 10 is 40, 4 times 4 is 16. I get a negative 56. This product is equal to this term. So I know there's no remainder. That tells me that x plus 4 times x squared minus 5x minus 14 is going to give me that product, which is also my numerator. Again, no remainder. Now, because this is a quadratic, I have two more roots that I've not identified. I know one root is going to be negative 4. That's where it crosses, this equation crosses the graph on the x-axis. So how do I find my other two roots? If they're real, my first step is to look at this, see if it's factorable. Can I easily factor that quadratic? Well, if you recall, the first thing you do is look for that constant and see if you can identify factor pairs in negative 14 that give you the sum of negative 5. Well, I know that the product of two terms, it's going to give me a negative 14. One must be positive, one must be negative. It's going to give me a difference of 5. So the factor pairs of 14 are 1 and 14 and 2 and 7. The only pair that's going to give me a difference of 5 is 2 and 7. Now, those will sum to a -5 only if 7 is negative. This is the factored form for this quadratic. If you use FOIL and area model, you'll see that that's true. So if I add on the end here my other factor, now I know that this is the factored form for this polynomial. I factored out an x plus 4. I factored the the solution to that. And I get these two factors. I know my x-intercepts, my real roots, are -2, +7, and -4. And if I were to graph this expression, I would see those real roots show up.